Okay, so I made some slides very briefly, just half an hour ago, sitting right there. So they're a little brief, but I want to describe some observations and long-term trends about the organization and structure of the Bitcoin blockchain as the technology evolves. So if you think about what is the blockchain for, so I think in a lot of ways it's one of the most innovative things about Bitcoin. So obviously it provides double spend protection in a distributed network with no central party to kind of bless transactions. And part of that comes, I think a lot of the security comes from the fact that there are many verifiers. So, everybody who's interested can verify. Anybody can run a full node, many people do. Exchanges, banks, wallets, power users, and lots of enthusiasts run a full node, and they're able to verify everything. So it's a kind of assay for Bitcoin, and it means that miners are really just service providers because anything they release in a block that's not valid would immediately be dropped by all of these nodes. So this kind of pervasive verifiability and verification is a big part of Bitcoin's security model. Now, of course, that makes things complicated and implies certain things. So all the transactions are broadcast, all of the blocks are broadcast to tens or hundreds of thousands of nodes, and when a new node joins the network, it has to catch up with history. So every new node downloads all prior history. So if you look at the mechanisms used, there's quite a bit of effort being put on over time in reducing the size of transactions and improving the efficiency of network synchronization. So, and that's because to properly verify the blockchain, you have to verify the history, and so first you have to fetch it. So losing the history or having a gap in the history would be a problem. If you don't have the history, you could be fooled into following a more recent fork of the chain or something like that. So far we've said that the blockchain structure implication is it needs to be compact. So I'm going to describe some early evolution. So originally Bitcoin used uncompressed public keys. So as far as people can see, if you looked at the code, that was because the crypto library that was used in the early versions of Bitcoin would just give you the elliptic curve public key as both x and y coordinates, so it's quite large, and actually that can be compressed approximately in half by just removing one of the coordinates and putting whether it's positive or negative and calculating it. So there's a simple equation that can be used. And so that change was made at some point in Bitcoin's history. Something else that was introduced later is hashed public keys. So the Bitcoin public keys are 256-bit kind of compressed points. And previous to some even more recent changes, the addresses are actually hashed with a 160-bit hash, so that makes the addresses smaller and easier to work with, while still preserving most of the security, except in a multi-sig situation, which we can get into. And while it makes the addresses more compact and easy to work with, to type in, to verify, it doesn't actually save space because ultimately the uncompressed public key, everything about the signature and the script to verify that the script is true still ends up getting sent on chain. So particularly with multisig and P2SH, there can be quite a few keys behind it, and you won't know when you send to an address if it's multisig or not, but that's convenient for the workflow, basically. But it does put the onus on the sender to include the signatures from all of the public keys, and that includes the public keys themselves as well. So then quite a lot of data gets sent later. So overall, this mechanism is actually increasing the block size slightly because it's sending the hash of the data, and then later it's sending the data as well, rather than just the data. So that's approximately the current state of play pre-Taproot. And Pre-Taproot, any script you included would have to be revealed. So if you constructed some complicated script, like Lightning is not that complicated, but it's a more complicated script with some OR branches in it. So nevertheless, you'd have to reveal the whole script, even if it has an OR in it, where technically you only need to reveal the part that returns true. The other part is kind of surplus information. And so one of the things that Taproot does, well, particularly Mast, so Mast is the observation that in programming languages, if you look at the tree of the program, you only need to verify whether a claim or a function is true, you only need to reveal one OR branch from the top level that calculates true. The other ones may be true or false, but it doesn't matter. Any OR branch that returns true is enough. And that observation allows you to save space, because you can have a kind of more elaborate program. And so there's a sort of general observation for Bitcoin scripts, which is that you have two parties engaged in a contract of some kind. And you see that with Lightning, that there's a person at each end of the route of the channel. And then there's something more complicated that happens if something goes wrong with the channel. Like you can't reach the other person, you need to forcibly close the channel. And so that OR branch is a kind of exceptional case. And 90-odd% of the time, you would actually close it collaboratively. So pre-Taproot, you have to reveal the whole contract anyway. But with Taproot and Mast, you don't have to reveal it anymore. So what you do there is the top level is just a multisig, and there's a hidden OR at the top level. So the point of Taproot, which is Greg Maxwell's idea, is that you can have a public key which just looks like a single signature public key, and you could have an optionally disclosed script that is committed to by that public key. And so if you reveal that, now you've got two tasks. One is to prove that that script is true and sign with the remainder of the public key. So that's the Taproot part, and with Mast it generalizes, so you can have more branches beneath it, and your task is just to reveal one that evaluates to true. So even this top level general arbitration mechanism saves quite a bit of block space, because if most Lightning channels close without needing the arbitration clause, it never needs to see the blockchain. Something else that makes the Schnorr part of the Taproot proposal more compact is the Schnorr signatures allow more compact multi-signatures. So a 2 of 2 signature looks indistinguishable from a single signature and takes the same space. So now with Taproot and Taproot and Schnorr in play, you can have a Lightning channel that looks to somebody observing the chain like a single signature transaction, and if it's closed collaboratively, you would not necessarily know that that is actually a Lightning channel. Now, of course, many Lightning channels are advertised, so you can find out indirectly, but it doesn't consume block space. Now, if something does go wrong, then you have to reveal the arbitration clause and basically prove to the blockchain that you have the right to close this channel. So that's an example of basically a trend I'm trying to draw from, which is that the Bitcoin blockchain is kind of compressed, it's using compact formats, and it's evolving to make that more and more the case. So, it went from an always revealed script, from uncompressed public keys to compressed public keys to hash public keys, now to multi-signatures that look like single signatures and escape clauses that are not visible unless used. So it's sort of getting smaller, and a pattern is emerging where the blockchain is only involved even in the intelligence about the contract if something goes wrong. But in the general case, the parties are mutually agreeing, because there's a threat that there's no reason for one party to dispute a transaction if the other party can anyway go to the blockchain and guarantee to settle it in their favor. So there's an incentive, or no incentive to artificially dispute. Of course, sometimes the other party is just simply unreachable, or lost their keys, or had a hardware failure or something, and in that case, you need to use it. Another part of Lightning in general is the hash lock, which is also increases the size of the script. And so it's basically a solution to the who goes first problem. So you want, both parties are tying up some Bitcoin in the channel, and they want to avoid a situation where one person commits funds and then the other one locks them up so they can't get the funds back. And so you need both parties to cooperate, and you want to do that without having to trust them to cooperate. So if I put funds in the channel and the other person says something malicious or walks away partway through, my funds could get permanently stuck in the channel. And so the hash lock kind of prevents that. And what it assures is basically if one party reveals the pre-image to the hash, that information is revealed to everybody simultaneously. So it uses the blockchain itself so that if you try to take a transaction you shouldn't have, you necessarily reveal enough information to the other person to contest it. So that is the current hash lock mechanism, which Lightning uses and also takes up block space. So it's another reason why you can tell that a Lightning channel is a Lightning channel. So there's a new variant of hash locks, which is part of the so-called scriptless scripts. And so it's basically an observation that you can get something with a similar functionality to the hash lock, that you can be assured that if the other party tries to spend the coins that you've multi-signed, that you will learn the commitment, the kind of pre-image inside the signature or the public key. And so in that way, you get the benefits of the hash lock without needing to use increase the script size or without needing to reveal it to the blockchain. So it's another way that the blockchain can create a multi-party behavior that doesn't create data on the blockchain. So it's another kind of compression thing. And so there's something Lightning can use. So this one doesn't really save on blockchain space. It actually increases blockchain space because the confidential transactions are larger. So confidential transactions, they're used on a few different, on like Liquid, which is a Bitcoin sidechain, and some other blockchains have adopted this technology as well. And it's not really privacy because you can still see the inputs and outputs to a transaction and explore them forwards and backwards in the blockchain. But it encrypts the value of the transaction, how many Bitcoins are being sent, so that only the sender and receiver can see that and verify that. And however, because it has a compact zero-knowledge proof, everybody can verify that that's the case, that there's no new coins created or destroyed by this transaction. Though the blockchain doesn't usually concern itself with destruction. You can always destroy coins if you want to by sending them to an unspendable address or losing your keys. So the main point is to prove to everybody, to miners, to everybody running a full node, that there's no new coins created by this transaction, even though you can't inspect the values. And there are a couple of different ways to do this. One is a Pedersen commitment. The question mark is what happens in the, so this technology works. It's using conservative crypto assumptions, so actually the same assumptions that Bitcoin uses by using ECDSA and Schnorr, actually. So it's, even though it's doing something sophisticated, it's doing it using simple standard building blocks that are the same things that Schnorr signatures and ECDSA rely on. And so there are two variants. So the question is, what happens if discrete log is broken at some time in the future? Decades in the future, turns out there's a problem with discrete log, or quantum computers get very powerful. It's a kind of worry in the back of people's minds. Personally, I think it's not that realistic, and those things are many decades away, but Bitcoin is built for the long term, so it's something people want to think about before they do long-term cold storage or before they put funds into a new script, or opcode, or behavior, extension behavior. And so the question is, what happens if the discrete log breaks down? These things are built using discrete log. And what happens depends on which method you use. If you use the Pedersen commitment, you keep your privacy, but you risk inflation. And nobody wants inflation. But of course, once you've assumed that you have value privacy, you may be unhappy about losing it in the future, because it would mean It's as if after some decades your bank statements became transparent or something. You're not going to lose money, but people can see how much money you had at a point in the past. And if you were assuming that's not going to be the case, you're also not going to be happy. And the Al-Gamal commitment, in that case you lose your privacy, but inflation is mathematically proven to be impossible. So there's a kind of unhappy trade-off where you kind of want both behaviors. And it's sort of mathematically known that you can't have both. They're kind of opposites. But Tim Ruffing managed to find a kind of cheat, which is a paper he published called switch commitments. And switch commitments are interesting because they start with the Pedersen commitment, so you have privacy. And if you see that discrete log is getting weak, you can switch to using Al-Gamal commitments. So you can prevent the inflation. So you can sort of say, well, let's assume that discrete logs are never broken in the time frame we care about, then we're good. If they do have a problem, we have a defense, as we can switch to Al-Gamal commitments. And then the only remaining concern would be, what if they're broken suddenly in a way that surprises everybody? But that's probably not so likely. So anyway, I mean, about the size, the transactions end up being maybe about 10 times bigger. There may be scope to make them smaller with more compact zero-knowledge proofs. The bullet proofs are actually, so the compact zero-knowledge proofs used in confidential transactions were kind of an inspiration for the bullet proofs. So, the people that developed the confidential transactions, Greg Maxwell, Peter Will, went to some researchers at Berkeley and explained the problem and asked if they had ideas of how to make them more efficient, and they didn't really, but they thought it was an interesting idea, and they they took on board the security requirements of Bitcoin, that it only wants discrete log assumptions and hashing and no esoteric new cryptography constructs. And after a while, they came back with bullet proofs, which is way different to what was asked for, but way more as well. It's a signature of execution, so it's a kind of advanced complex concept that you can actually make a proof that a program returned true on some data without revealing the data, and come out with a relatively compact proof. And the bullet proofs are log scaled, so the size of them doubles. It gets like 1 unit bigger for each doubling in the size of the script. So you can make surprisingly large scripts with still a relatively compact proof, but not an enormous program. And the execution is not helped by this. So the verification and proof construction time is still relatively lengthy. So it turns out that the bullet proofs can be used to compress the Pedersen commitment type of confidential transaction, but not the Al-Gamal one. So that takes the Pedersen commitment down from a couple of kilobytes to 700 bytes and leaves the Al-Gamal at 2 kilobytes. So I think for size reasons it would be desirable for Bitcoin to, I think Bitcoin would want the Al-Gamal commitment. That's my view on that trade-off, possibly with a switch commitment, but would probably want smaller proofs than are currently possible, because 2 kilobytes is quite large, even if it counts as witness data. So it's got the 75% discount of the signatures. And so you can see this if you're interested in confidential transactions and to see what it looks like in a block explorer or in a wallet. You can try it out on a liquid sidechain with Bitcoin. But the technology risk and the blockchain size expansion is all absorbed by the sidechain, because that's one of the points about sidechains is to have a kind of security trade-off where you can build different things outside of Bitcoin, but still connected to Bitcoin via a peg. Something more adventurous that could be considered as a sort of longer-term evolution for Bitcoin is to use the snark or bulletproof-like technology to prove that the block is valid. So how you prove it's valid today is you receive the block and you verify all the signatures, you verify the formats, you verify none of the coins are double spent, and then you verify the proof of work. So the concept with the proof of block validity is instead of running that code to verify the blockchain, you verify a proof that that code ran on the transactions in the block and return true. So the problem with that, though, is as you can imagine, the code to verify a block is a lot of code. It includes, hashing and signature verification, and bulletproofs are kind of bit-level circuits. So the number of bits to be verified and ANDed and ORed together to make a circuit to verify a whole blockchain is pretty enormous. So even with the log scaling, that would be large and expensive to verify. So, excuse me. So there are also arguments that you still want to receive the data in the block. So I think people started with this concept assuming, they started assuming that they wouldn't need the chain history because you can prove a program returns true without revealing the data. And that's true, but it creates a risk that the miners collectively, or whoever constructs the proofs that go into the mined blocks, will share that data with future miners and with users. So I think it's potentially risky to rely fully on these proofs. You see, if you don't, if you rely on a collection of people to manage the proofs, they could end up not sharing it or losing part of the data. So generally the conservative assumption is that still everybody needs to see the data. And so if you do that, then the compression is not that small. Like a Bitcoin block is about roughly 50% signatures. So at best it would get 50% smaller. And Bitcoin already has ways to compress signatures. So, excuse me. So one of the things that's in flight at the moment is the Schnorr signature validation. So that can be batch verified. So you can sign. So I said that that Schnorr has batch. Compact multi-signatures composed of n of n signatures. It turns out that works across multiple inputs to a transaction, and even all the transaction inputs in a block could potentially be batched. So if you follow that through, it means that Bitcoin can, effectively already get most of the compression without involving expensive zero-knowledge proofs, just by opportunistically batching and making compact multi-signatures from the inputs. So, so I think some other chains call these things ZK rollups, but it's effectively the same thing. So I think the observation here is that the Bitcoin blockchain is already quite compressed, that you anyway need the data to assure yourself that miners will share in the future. And I think you could argue that you could have a new profile of SPV where some people are fully SPV, some people are verifying the blocks but not receiving the data, and then some people are receiving all the data as well, so long as it's enough. So I'll talk a bit about simplicity. So simplicity is a new sort of next generation smart contracting language for Bitcoin. And it's very low level. It's a kind of extensibility language. So I've described it here as a microcode for Bitcoin opcodes. So for example, if Bitcoin had simplicity today, the Schnorr signature could have been implemented as a program rather than as a soft fork. It's very low level, so it's kind of bit level logical operations. And it's in a formal language, so you can make statements and verify things about the correctness of it. One of the interesting crossovers is that because it's sort of bit level and formally defined, you could actually, there needs to be more development work here, but in principle you could compile a simplicity program into a bulletproof. And that's interesting because one of the gaps with bulletproofs or complex zero-knowledge proofs is the risk that the person designing the circuit made a logic error. So now you have a proof that something is correct, but the program doesn't quite do what they think it does, or the circuit's not. And the circuits are large because they're very low level, and any kind of moderate program turns into a big circuit. So simplicity adds the formal verifiability for the specification, and that should survive. You should still have the semantic provability after the compilation. Yeah, so that's the point about that. So I'm thinking also that, I don't have a slide for this, but that there might be a kind of shorter term VLIW, thanks, kind of opcode, where you have a kind of compact zero-knowledge proof using bulletproofs that packages together common choices like if something is spendable after a given height, what height it's spendable, some optionality, and then you could make a simple bulletproof that proves whether it's illegible without revealing that information. So that would be another step towards reducing information in the blockchain. And so you could tune the site, the amount of data saved by doing that with the size of the bulletproof. So, but if it's, if it's targeted and you design it correctly, that's another possible step. So that's it. Last slide, and I think we could take some questions.
Thank you, Adam. Let me start with the first question. I will make a very simple question because I've been intellectually challenged. Maybe some others too. You answered this very nicely earlier today, so I will ask just the obvious question. Where will the Bitcoin price be in 5 years?
Okay. So my answer earlier, by the way, was 500,000. Okay. Which was drawing from gold, basically, but it's kind of a random, yeah.
Good evening, Adam. I'm quite interested about Blockstream Liquid and the potential of the network to grow. Maybe you can share some way to improve the network effect within the Liquid network, and maybe something you guys are actively doing to do that.
Yeah, I think there are, with any technology, people the street finds its own use. So we've certainly seen community things evolve. So some people said that they use it. So I would say generally it's fair to say you shouldn't look to do long-term cold storage on Liquid. It's more transactional. But apparently some people are using frequent dollar cost averaging in Liquid because the transaction fees are low. And then they'll cold store after some time or after some threshold. So that's kind of one simple use case. There's been quite a bit of organic things going on. So SideSwap, for example, was an interesting wallet. It's a liquid wallet, basically, and also handles Bitcoin peg-ins and peg-outs and conversions. But particularly it has a trustless OTC, like trustless atomic swap between Bitcoin and stablecoins in liquid, so it avoids the who goes first. And interestingly, they also implemented a trustless limit order. So they have what looks like a central limit order book, but it has no custody. So a user can use their app on a smartphone, place a limit order, they've still got the keys, and somebody can take the limit order and it gets broadcast to the chain. But, and then it goes back to the user. So it raises the prospect that you could, kind of place out of the market limit orders for coins that you actually have in cold storage effectively without risking exchange custody. So it's an interesting concept for exchanges. Of course, managing the risk of hot wallets is always a problem for exchanges. So if they can persuade users to take responsibility for their own coins, that's generally good for them. And it might also improve liquidity because if people are willing to put extra limit orders on the order book that they're not expecting to get filled, maybe that's such a low probability order that they're not willing to risk exchange custody for it. But if they can place a limit order that will only, how it works basically is that there are Bitcoin inputs and there are stablecoin inputs. And the transaction won't clear unless, and so in Bitcoin, the value of the inputs has to equal the value of the outputs plus the fees. In Liquid, the value of the inputs of each type has to match the value of the outputs of each type. So if I want to buy Bitcoin at $25,000 and hope that happens, I can put a Bitcoin there and put a phantom transaction paying me $25,000 and just leave it on the order book. And the only way that can be spent is if somebody pays it, basically. If somebody's willing to take that offer. So, and there are also some, there's another one called TDEX, which is a bit more decentralized version of the same kind of trustless swap. So I think seeing those kind of trustless settlement things integrated in more places would potentially be a driver, because it's definitely something that anybody who does exchange trading or manages a fund with exchange trading thinks about, which is the risk that the exchange faces a loss. And so this would be one way to avoid that. And the exchange can mix custodial and non-custodial orders. They can, if they need to match a non-custodial order with a custodial one, they can just act that part from their own hot wallet, basically. So I think integrations, and the Blockstream mining node is also a big driver for Liquid adoption. There's different kinds of exchanges want access to it, and that's the way to get access to it.
Hey, you mentioned privacy loss problem with LGML. Is it immediate privacy loss, or will it last for some years?
Well, I suppose it depends how catastrophic the discrete log failure is. If it requires a very expensive computation for each time, perhaps it's too expensive to attack them all, but some things get attacked. It's kind of a hypothetical situation because it's very difficult for us to think about today how that could be just mathematically broken, for example, right? So the current thinking is it requires some kind of, enormous multi-decade leaps in quantum computers and a big quantum supercomputer or something. So it's not clear how that will play out. And I would guess it's not going to happen for a long time, if ever, but we'll see.
Could you share with us your outlook on different solutions about programmability on Bitcoin? Like, we have different developments, RSK, we have RGB, we have Simplicity, we have Taproot, and is it like that you see that one of them may, like some of them there will be winners and some will disappear, or all of them will have their place because of different trade-offs, like maybe you see some other solutions that I did not mention?
Well, I think there's an interesting distinction between layer 2 and the main chain. So, particularly, layer 2 is fairly permissionless. Like people can make different approaches and try them in parallel. But of course, there are always, so far at least, there are always security trade-offs with layer 2. And in terms of what technology makes its way into the Bitcoin main chain, like which new opcodes, that's like very conservative and slow-moving. So defensively so. And of course, some people sort of prefer that Bitcoin ossify. Like, if you talk to investors, they'll say, what's your primary feature request? And the answer is, well, just don't break it. And so some of those people are not very excited by, fancy things or even Lightning. They're looking at the digital gold use case. But I think coincidentally, simplicity is a candidate technology to actually get to more final ossification, because it gives low-level extensibility so that you can implement opcodes directly. So it could almost be kind of the loss of fork. And I think that's quite attractive because it means that you can get confidence by making formal proofs about the behavior. And if there is a client upgrade, it's for efficiency reasons, not for verification reasons. So it's sort of forward verifiable today. So the SPV problem goes away. It's just how efficient is your node. If you have a very fast node, maybe you don't need to upgrade in the same way. So that brings in new kind of flavor or capability. So I think that, of course, simplicity is, we hope to have it in Liquid later this year. There have been a few developer preview releases on branches of Bitcoin and of Liquid. But I think realistically, for something as elaborate as that to make its way into Bitcoin, it's a multi-year kind of undertaking. If you look at Schnorr signatures in the Taproot, for example, I was discussing those in 2013 on IRC with other developers, and we only got that very recently. So it's that was 8 years or something, right? So a long time. But I still think it's an interesting solution, because if you like the opcodes in Bitcoin are kind of like a machine programming language, a RISC machine, and if you want to evolve the RISC machine, there's going to be some discussion about which opcodes play well with others, as well as the security. Just if you were talking about adding new opcodes to the RISC-V opcode set, I'm sure that would generate a lot of design discussion in the RISC-V community. So you have that kind of thing, where simplicity is saying, well, we'll just add microcoding, you can build whatever you want, and the definition gets a bit lower level. But in a way, it might be, so what I'm saying is it might actually be simpler to say, well, we want extensibility, as long as the formal provability is there, than to have a discussion about which opcodes are most useful.
Okay, the last question here.
Hi. I think we got the answer by you omitting the topic altogether in the future of the chain, your presentation. What is your opinion on covenants and the whole drama around BIP 119?
So, in effect, I think you could implement covenants directly in simplicity. So simplicity, if somebody's concerned about covenants, and I'm not personally that concerned about covenants, the concern historically had been that it could lead to a grey goose situation if you had too many complicated rules and a mistake was made. But I think the view of technical people looking at this stuff has evolved. So covenants were first described in 2013, I think, by Greg Maxwell on the Bitcoin talk forum. And at the time, he was talking about risks. But I think since that time, thinking has evolved about it. And so I think, there are two versions of covenants. There's a kind of recursive and non-recursive. And coincidentally, Liquid already has, for a few years now, had one of the versions of covenants, the CS, FS, and CAT type of covenant. And in the last few months, we released an upgrade to react to developer feedback on the initial version. So basically, people found it cumbersome to deal with because the way you would write covenants is you'd have to sort of print the script on the stack. So you'd have to do a lot of serialization to create it before you could verify it, and that was difficult. So we added a lot of introspection opcodes, about 30 different opcodes to be able to, firstly, opcodes to take a string and add it to a hash, so a rolling hash opcode, and some introspection opcodes to extract and put on a stack different pieces of information about a current transaction. So those were reactive to people writing complicated scripts in it, like automated market makers, which they made, but they said that was a lot of work. It would be simpler if I had this opcode, and 64-bit multiply became an issue for some reason to do with the values and calculations. So we added a bunch of those. It's quite a collection of opcodes, you know, like 30-odd opcodes to do that. So I'm not sure that Bitcoin likes to do things that are kind of more incremental changes and smaller. So I'm guessing that version is maybe too complicated, but at least we did some, some developers got some experience of using it and learned some things, so it might inform which variant is ultimately chosen, if any. So I think there are like 5 or 6 different versions that people are discussing at the moment. So I think the discussion is more, at least the technical discussion is mostly about which version is more elegant and fits in with the other opcodes and has good security guarantees and provides the functionality which is missing at the moment. I mean, one functionality that is kind of in the wish list for Bitcoin in a way is the any previous out. So it's a opcode needed by Lightning to make a more efficient version of Lightning, L2 Lightning. And so there's the interest to have APO or something, or the capability to do APO-like things at the same time. So if the covenant mechanism has an efficient way to do something equivalent to APO, that would be probably beneficial, for example.
So with this, we've come to an end. Thank you very much for your splendid presentation, Adam. Really appreciate it.